We're back. Yeah, everyone's back. Basically. I mean, Eric doesn't come in. Yeah. Well, Eric wants to say Eric is coming very fine.
I'm recording this, so I don't say anything like incriminating. You know? I mean, I don't think anyone will ever listen to it, but I mean, still, just to let you know. I actually didn't say, right? So it should have said like.
Maybe the volume's low again.
Well, that's the last time that I've been in conversation about the Oktoberfest.
Yeah, yeah. So that's the problem. Let's see. This Chris Mason.
There's a lot of talks. I didn't go to as many as everyone else did.
Probably too many. There's some that you said it's really interesting, and there's some that can't really follow.
I really felt like the way it's set up, it's like there are about 20 to 30 seminars going on at a time, and you just choose which seminar you want to go in. And I don't have that enough. So it wasn't.
Okay, that's on. I don't know why it didn't. Let me do.
Well, they were good.
Oh, sharply.
Let's get it like.
Oh, that's how it goes.
So Eric, so they did a tech presentation on Tuesday, she's presenting on Wednesday. And Ashley got like, wow, the profile that she got from Shanghai was wrong. And I was like, when I saw that, I just got it wrong. But then I got to figure out like why it's not working. So she was trying to fix it and get the right breath, but I think it's not that anything about who did it. So. I thought there was stuff. Yeah. Maybe there next year?
If I.
Oh,
Okay.
there's something about from this homework. So, so the correlation function thing. So he shows like this plot, right? And then it's got a straight line right here, and that's the surface of the phases. So when that's a straight line, it means you have like sharp interfaces. And the slope of that's the surface to volume ratio. You can calculate it if you want, but I don't have that. But basically this, when you have that straight line, it means you have sharp interfaces. So there's a problem like this, the whole point of the spinodal is to introduce this like interfacial term, like you have a diffuse interface, like you add in this kind of gradient, interfacial gradient thing into the free energy, or like this term, I guess. So anyway, that means there's no sharp interface. Yet his correlation function shows a sharp interface. So that no one figured that out, but basically that's like a disagreement. And the reason is, so I think if he, well, actually it's for both the simulation and for his machine learning thing. But the machine learning is like, it's going to be like 1 or 0. on or off, so you have to have a sharp interface. Machine learning will give you a sharp interface no matter what. Because it's 1 or 0, it's going to end up just giving a sharp interface. Anyway, so this shouldn't be a sharp interface. It shouldn't have a straight line here. It should be like a gradual, there shouldn't be any linear part to the curve at the small sizes. For a spinodal, it should be just a swooping thing. Like spinodal doesn't have a sharp interface. That's one of the main differences between spinodal and nucleation and growth. I mean, nucleation and growth, you have a depletion at the surface, so you get a sharp interface. Anyway, I thought I'd mention that. Because I graded those just like yesterday, so I finally graded those things. But anyway, otherwise, I think it was okay. People didn't, like here, like I wanted you to say like what the CIJ, like what they are. Like C11 is the tensile. I mean, some people said that, and then C22 and C33 are the other direction tensils. And then the 4-4 is the shear, right? That's a 4-4 is like a normal shear modulus. And then when you have the, like, let's see, 4-4 is a normal shear modulus, and if you have them mixed, that's going to be like if you have a 1-3 mixed or 1-2 mixed, that's a normal force.
The Wikipedia for the tensors also pretty good example showing those.
Okay, so like if you pull, it's like if you say you push something and it squishes out sideways, right? So like gum, so you have that's a normal strain shows up with your tensile force. So that, and also like in fluid flow, like when you push a polymer through a die, it swells out. It's called die swell. So those are called normal forces. So there's a normal stress coefficient. There's a normal stress coefficient. It's like a viscosity, but it's for this thing like this swelling out. The harder you push it, actually goes with the square of the rate that you push it. So it's like a strain rate squared versus a strain rate for the normal Newtonian viscosity. Anyway, so there's a reason for all those things. And if you're in some nuanced material, then you'd use the different ones. So anyway, people just kind of didn't define those at all, or they just maybe messed up a couple of them, like the normal force one. You have to kind of really think about, it's confusing when he goes to 1 to 6, and then you have to figure out what those mean. Like they don't mean what you'd think they mean. Like 2-3 is not the shear, 2-3 is this normal thing. So and if you go 2-4, that's like if you did a tensile stress and you ended up with a shear strain out of it, which is possible. So if you think about, say you strain, like if you do like this, you can get shear banding in metals and in polymers too. So if you pull it and then it yields by these slip planes that are at 45 degrees, so that would be like a 1-4 or something, or 1-5 modulus you get from that. Yeah.
So these are kind of just from looking at it geometrically? Or
Yeah.
Could you know that just from like?
It's just from the tensors, like what the thing is, but then you also have to know like what a Young's modulus is. I mean, you didn't have to say it was a Young's modulus, you just say like it's this stress and that strain. Each one has two, each one's a tensor, so it has two directions to it. Right. So you have a force and area applied, they can be in different directions. And the same like the way you pull it and then the direction that it changes. So anyway, it's complicated, but it seems like the two nomenclature with the two things, which he calls a Voigt nomenclature at some point in that paper. Voigt did a lot of mechanicals models, I guess in the 1800s, VOIJT or something. So there's a lot of Voigt models for mechanical systems. So I mean, there's Maxwell models and Voigt models for relaxation stuff. So anyway, not that I like continuum mechanics, but basically it's good to know when you see the C12 what it kind of roughly what it means. I think otherwise you won't understand like what he's doing in the paper, right? I mean, you can't, and then it's not just this paper, it's like 2 papers where they use that, right? So looks like it's a popular item. Anyway, that's it. That there wasn't the other part, like this thing is just so involved. I think it basically took anything that you said, you know. But some of you said better things than other people. I think I gave extra points or you said something kind of coherent, but it's a pretty difficult subject to talk about. I think anybody finds it difficult. So I just wanted to get your feet wet in it a little bit. And you could see, I think at least you found out that the Wikipedia, the Hashimoto and this paper have like 3 completely different sets of equations that they're all calling the same thing and have to figure out the nomenclature, the symbols change, and then the whole approach seems to change a little bit, you know, like where he puts the del in the front or inside the term. Like, I guess that has a difference. And you have to kind of figure out why he did that. But anyway, so hopefully you learned something from that. That's it, I think. But anything else on that homework? I didn't really go through it on Monday, Tuesday, but hopefully it's all right. Yeah.
So I guess I'll talk to you about it.
All right.
Or whatever you want to.
All right.
Thing.
All right. Anyway, there is that thing that like this shouldn't be a straight line. And I think the only reason it's a straight line is because of this machine learning thing. It's going to end up giving discrete phases, you know, which will have an interface. So there's a couple problems with this correlation function he doesn't mention, you know, that weren't brought out in review. Anyway, so that's that. We can bury that. This week's, let's look at this week's one here. This week's is just, it should be simpler, but every time I say that, it's harder. So this is literally like a 3-page paper, like 3 or 4 pages. So it's short and it kind of gets to the point. It's a simulation, but it's not. Anyway, the first thing he does is he goes through this. I went through last time this Gibbs nucleation theory. He called it the classical nucleation theory, CNT, he calls it. There's also the carbon nanotube. But anyway, so it's like you have the bulk energy. So this would have enthalpy and entropy. Then you add in terms to it. And in this case, he's adding in the surface term. So this term is cubed, that one's squared because it's volume and surface. These are for spheres. And then if you take the derivative of that, you're going to find out that you have like a kind of a magic size where that free energy goes to, let's see, does he plot the free energy here? No. So the free energy goes to 0 at some point. That's versus mole fraction. So the bulk is, as you change the size, so the bulk is growing faster than the surface. The bulk is negative, so that favors mixing, and this is positive, so that favors demixing. So the surface is going to favor demixing. So when you get to smaller sizes, this becomes unfavorable, and it increases the delta G, makes it positive. And then at large sizes, this thing, I guess, anyway, somehow they act oppositely, and there's a maximum in it. And if you take the derivative, you can find a size, and that size is this critical size. And if you plug in the critical size back into this equation, so you do the derivative, plug in the size back in, and you get this critical free energy, which is a free energy, like a barrier free energy to form the phases. And if you want to know the rate of growth, you plug that barrier free energy into like a Boltzmann probability thing, and you have a thing like AK would be like the collisions, number of collisions that the molecules have. It was a gas phase would be like collisions of the molecules coming in. So the kind of the frequency of collisions. So this is a rate of growth, the frequency of collisions, and the probability that the collision leads to a crystal has to do with that barrier energy. And the crystal grows at that rate, depending on what this barrier energy is. That's kind of the full critical nucleation theory thing. So you get an optimum size below that size you don't grow phases, and above that size you grow phases. That's the general idea. All right, so you notice that this is like cubed and squared because this is a bulk equation for homogeneous nucleation. So you have a single phase and then suddenly nuclei form out of it spontaneously, which isn't really how nucleation and growth works. Like spinodal works that way, but nucleation and growth usually need a seed to grow from. Right? So there's a flaw in this whole system. Well, you need this critical size seeds to grow the crystal to begin with. In spinodal, you don't, and nucleation growth, you do. Then the other option is like once you have seeds, then it isn't like 3 and 2, it's 2 and 1. So you have like platelets that form on a surface when they spread out, right? So that's heterogeneous growth. So then you also can take the derivative of that free energy. So this would be squared. This would be to the power 1, and you'd be looking at circular platelets that grow that have a fixed thickness of kind of like one atom. So you add in like one layer of a crystal on. Anyway, so that leads to a different answer. It leads to half the size. So the heterogeneous will give you half the size, and it gives you kind of half the free energy, a little bit more than half the free energy. So you get a lower barrier energy and you get a smaller size when you heterogeneous nucleate. Because the lower barrier, it happens first. So if you have an option, you're going to do homogeneous and heterogeneous, you'd always crystallize on a surface if you could. So if there's dirt present, that's the kind of crystallization you'll get because it's half the energy basically, or half the size. So he goes ahead and he talks about this bulk equation, and then he shows his simulation, which is heterogeneous nucleation. Like he's got the crystalline calcium carbonate, calcite, and then he's got what he calls amorphous calcium carbonate, ACC, or hydrogenated amorphous, which is H-ACC, kind of at the surface. He can vary the concentration in this. So this is a whole simulation box, and he's got some concentration here that goes up to 100%, which would be the same as a crystal. And then he measures the energy at the interface of this thing. So since water is involved, so when you have a crystal, so the surface energy of the crystal involves like how many bonds there are at the surface. So I went through, like, if you have different crystal faces, you have different numbers of bonds, so the surface of the crystal has different energies. So you always will have the surface with the highest energy will have the highest surface tension. And then that should be the one that grows like the fastest, like the 111 crystal in silicon and diamond cubic would grow the fastest, say, for instance. So anyway, usually like an FCC or HCP is kind of like the 111 plane because it's got the most bonds. And then the strength of the bonds, the higher the surface energy with the higher strength of the bonds, higher the modulus, higher the surface energy. There's a bunch of plots from the book that show kind of the cohesive energy density of the crystal defines like what that surface energy is going to be. So the idea is like you have like the crystal stops here, and then you just have bonds, half bonds sticking up that want to bond but can't, and that's what creates the surface energy in a crystal, right? So anyway, so in this system, he's got water, so the water kind of placates those calcium carbonate bonds that are left dangling. So when you have low concentration of calcium carbonate in this amorphous ACC, hydrogenated ACC, then you get, if it's low concentration, you get a lot of water. This is a plot of the water density as a function of direction from the surface. So it gets peaks. This kind of plot you can measure with reflectivity, like you can either do neutron X-ray or you can do lipsometry with light. So you can measure the density profile normal to a surface with X-rays. You bounce a beam off the surface and you calculate from the reflection curve as a function of the angle of incidence. You can calculate these profiles. Right. So these can be experimentally determined. He does it, and it's pretty easy to get that in a simulation. Just say like, what's the density across this of the different components? Right. So this can be verified experimentally. I mean, with neutrons, because you can tag water with deuterium, and deuterium has the contrast between D and H. Deuterium and hydrogen is the highest for neutrons, so that's like a natural thing to look at a water system to get this water profiles to do neutron scattering at this or neutron reflectivity. Anyway, so it gets a lot of water when there's no calcium. When the calcium competes, the water drops. And that's why the calcium concentration impacts the surface energy, because when water can't placate those bonds that are dangling there, then the surface energy goes up. So these calcium carbonates displacing the water, but it's not kind of crystallizing, so it just leads to a higher surface energy as he puts more calcium carbonate in. So that's kind of what he has, and there's some kind of saturation effect to that. So this looks a lot like the Langmuir absorption curve. So you're going to have a fixed number of sites, and then once you fill up those sites, the game is over and it just reaches a plateau. Right, so you'll see the same kind of curve, this kind of sigmoidal curve for absorption of gases onto surfaces. So whenever you see this kind of plateauing out for a surface effect, it's mostly got to do with that you have so many fixed number of sites there and they've filled up. Right, so that's kind of the picture that's going on here. So I think that's kind of, there's not that much to this paper. I just thought, I kind of know this place where they're from, so I thought it was kind of interesting. He has the Gibbs nucleation theory at the beginning. Oh, and also he has a nice discussion about crystallization from solution here. So he kind of goes through the various things that can happen. So basically you have to supersaturate to get to crystallize. And if you supersaturate at the interface, if it's in solution, then there's various things that could happen. You could form a polymorph. You can directly convert to the crystal. You can form a polymorph that's of a lower stability, like Ostwald ripening, and then it can convert to the crystal. You can do spinel decomposition at the surface because you're deep into the supersaturated. So you could spinally decompose at the surface, and then that could form those phases, liquid phases, the spinally decomposed can form the crystal. So this exactly the same argument is presented for drug crystallization, for polymer crystallization, and for calcium carbonate crystallization. So it's like the same story over and over again, so it's like deja vu all over again, right? So anyway, this pre-nucleation cluster, so this business isn't exactly new, and people will continue to argue like what's going on, and there's no way to really measure it. So they just say they'll argue it, that without much evidence. And so he's kind of in this idea that none of that stuff happens, and he just has this uniform hydrogenated ACC layer, and that he can predict this crystallization behavior. So it's not, anyway, it's kind of interesting. Calcium carbonate, it's used for a lot of things, but it's not really like high tech or anything. So I thought it looked like it was kind of a simple paper, so hopefully it won't be too bad. First paragraph, so just kind of look through that reasoning. Equation 3. That's part of this thing. Oh, he's just saying the chemical potential. So the chemical potential is usually like KT ln of the P ratio or of the composition. And here he's got the activities of the components that are crystallizing, and KSP is a product of the components, blah, blah, blah. So this is like this is the change in, so it's delta mu. So one of the mu's would be KT ln of the composition. Delta mu is a difference. When you subtract two logs, it becomes a ratio in the argument. It's like ln of pi. A means all the A's multiplied by each other. A1, A2, A3 times. And then, so this divided by kappa would be like, or by K would be like minus ln of K, right? So basically you can work out like where this came from. It's the same, we had this before for a question in the homework, like where does that kind of expression come from? So hopefully that's not too bad. I have equation 4. Equation 4 is, so equation 4 is coming, delta GC is from the derivative of this thing. Set the derivative of this to 0 and you'll get this thing. The gamma here is the molar volume of the structural unit. So he divided by the volume. In other words, this is a volumetric free energy. I mean, it's per volume. You have to divide by the volume. So the molar volume of the unit is going to be 4/3 pi r cubed, I think. And then, so you should be able to figure out from taking the derivative of this, get that expression for this critical, set this to 0, find the magic R value, then plug the magic R value back in this equation, and then solve for delta GC, and you should get that. So that should be an interesting exercise. This is what I just said about the interfacial energy increasing. And then this business, so, I mean, I think general consensus now is that you can never ignore the organization of water because there's so many. So entropy isn't by volume, it's by number. And there's a lot of waters in this thing. And he even says hydrated calcium carbonate. And he even says like the water organizes at the surface to placate those bonds. So I mean, how you could ignore the entropy of the water in that kind of situation after saying all that is really pretty hard to justify, right? Because he's saying that it's the organization of water that's blocking the bonds. He demonstrates in a simulation that the water organization is destroyed by the calcium carbonate, and then he ignores the organization of the water as a contribution to the free energy, which there's gazillions of waters there. It matters like how many, not how big. So anyway, so water could be the whole system here. It could absolutely change the surface energy. You're going from, as you increase the calcium carbonate, so you're going from ordered water, which would have a bad free energy, to disordered water, which have a good free energy. So it should have the opposite effect on the free energy, I guess, with what he observed. It should lower the surface energy to disrupt the water. So, I don't know. Anyway, at least the way I'm thinking about it right now, but explain how the critical nucleation barrier is calculated in figure 4. Figure 4. 1, 2, 3, 4. Oh, so he plots that critical. So he does a derivative, gets the R, plugs the R back into the equation, and gets the critical. And then he plots that against mole fraction. So that's how you get that. And then he plots it. What's the difference in these two? Supersaturation. Let's see. Critical nucleation barrier of formation calcite interface. Different mole fraction. For supersaturation, different supersaturation. Supersaturation 3 green circles and 4 purple squares. And B, supersaturation directly approximated to the mole fractions, or using a driving force calculated from the free energy. Difference between the ACC phase. So you've got 2 ways to get it, I guess. That's the point. I don't know, I didn't actually look at this that much. But basically, he's got 2 ways to get it, and he's comparing the two. This is the way we did it. And this is a different way. Just saying you can calculate the free energy. In a simulation, you can calculate all the interactions of all that. It's a molecular dynamics, so it has all the interactions of every molecule in the system. And you can sum those up and get a free energy. Then you can subtract the free energies of the top phase and the bottom phase, and then say that the difference between those 2 free energies is the interfacial free energy. So I think that's what he's done here. And I guess he's comparing these numbers. They look to be different. Like this is yeah, they're different in value, quite a bit different in value. So, but the shape is kind of the same, but the values are different. So I'm not sure, I didn't actually read how he explains that business. That's kind of an obvious thing to do, I guess, to compare the 2 approaches. Anyway, you can look at that. There's a question that talks about it. I haven't really looked at that yet. What's the difference 4A and 4B? I said what 4A and 4B difference is, but why is the value different? The value is quite a bit different. I mean, it's more than an order of magnitude different. So, I mean, there's something that this is accounting for that this isn't accounting for, which might be the water. could be the water, it could be the difference here. So anyway, you can kind of look at that. Hopefully it's a good enough little exercise. Any questions on that thing? Hopefully it's okay to do. All right, so let me get back to whatever we were doing. Let's see. So talked about grinding things that you kind of reach a limit. We can't grind it anymore because the energy goes up too high, right? Basically, in other words, the surface, when you form the surfaces, is a surface contribution, and you can't grind things anymore. It's not a linear dependence because it goes with the square of the size. So I'm going through kind of how you get this excess properties, and then we figured out somehow from that the Laplace equation, which basically says that you're going to have like two. If you have a droplet, the pressure is going to go with 1 over the surface tension divided by the size of the thing, or it would be like this c, the curvature. So curvature would be 1 over r. So in other words, if you draw a circle at a surface, the radius of the surface and the curvature is 1 over that radius. So that the higher the curvature, the smaller the radius. For a smaller circle, you have a sharper curve. And so Laplace equation just says like the pressure, and you can kind of measure that for this would be like for water. Basically, if you go to a micron sized droplets, you get a huge pressure in those. Right? That's kind of the idea of the Laplace equation. The curvature, because you can have surfaces that aren't spherical, so you could have two like X and Y circles that would be tangent to the surface of two different radii. Right? So you'd have C1, C2. And then if they're the same, so it's actually circle shaped, you have like 2 times sigma times C, or times 2 sigma divided by R would be the pressure difference between the droplet and the. So this works also for pressure and in phases, right? In solid and liquid phases. What else? So you can add that, and so basically the Gibbs idea is to just add that into the free energy expression. So you have the normal free energy, like G's V VDP, TDS, and then G's S minus SDT, VDP, and then you add in a term for the surface energy. That's a positive, it increases the free energy, and then it's going to be relative to the area that you create at the interface. And then this is the bond thing. So basically, the more bonds you have at the surface, the higher the surface energy of that crystal face. From that, and also from this idea that you can get the volume of the crystal. So for cubic, if you had 6 sides to a cube, so 6 divided by 3 would be 2. And then the radius times 2 would be the diameter. So the diameter times the area would give you the volume of the cube. So this works for any crystal, any shaped crystal. This idea that you can calculate the volume from the radial normal to the center, distance to the center from the face of the crystal, right? And then you can use that plus this idea that surface excess is going to be the sum of the areas. So O is A, and then the surface energy. And then you can minimize those things, and you can get this this idea that the distance from the center to the normal from the face to the center is proportional to the surface energy. From that, you can figure out what the shape of a crystal is going to be. Like if you have a high surface energy for surface, then it's going to preferentially grow and will grow into a rod. Basically, you have one of the faces has a much higher surface energy than the others, and you go a rod structure. And if 2 of them are normal and they're a higher energy, then it'll grow a sheet structure, a sheet crystal, right? And then any shaped crystal you can figure out basically from this kind of arrangement. Just figure out what's the size, distance from the center to the normal to the center of a face, the distance, and then compare it for the others. You can get the ratios of all the surface energies for a crystal that way. Right? That's the idea. And then That's the Laplace equation. Then he shows plots versus the periodic table type thing. So you have like the transition metals. So you have groups, and then you have periods like X and Y for this. And then within that you have these blocks, right? The S blocks, and the D block is the transition metals, like this middle part, right? So these can all have different ionization states. And then so those are of interest, I guess. Those are like primary interest things. So anyway, so the bonds are stronger in the D block. Because the bonds are stronger, you get higher surface tension. And then if you look at the heat of vaporization, you get higher liquid surface tension. And then so everything kind of goes with the cohesive energy density. The melting temperature, surface energy goes up with melting temperature. It goes up with vaporization temperature. Right? So everything kind of ties in with that. And he gives us an equation which is similar to the this kind of Gibbs thing where you swap out T delta S for delta H over T is delta S. So you end up with T delta H over T, which and T would be the equilibrium T, because you'd have like delta H minus T delta S, set delta G to 0, then you can solve for delta S as delta H over T, T at the equilibrium. So T equilibrium is T star. You have just delta G is delta H, 1 minus T over T star. So this is the same form. Surface energy, 1 minus T over T critical, like the vaporization temperature, equilibrium. Then that should be linear in that, but it's some 1.2 for this for some reason. And I think he shows that somewhere, but that's just like a general behavior. And then I went through last time the idea like contact angle. So you can think of this as a surface added per area, or you can think of it as like if you have a soap bubble, then you pull on the soap bubble laterally, then you have this length and that length. Those are the opposing lengths. And the force will increase proportional to the length. And as you pull this down, it's the surface energy that defines the force here. So you have the force divided by 2 times those lengths gives you the surface energy. So it becomes like a force per length. So force times distance would be energy. So energy per distance times distance would be area. So it's energy per area or force per distance, right? Sometimes it's easier to look at surface energy as force and distance. Sometimes it's better to look at it as energy and area. It's the same thing. That's kind of the point of this. Anyway, so if you for this contact angle business, it's much easier to deal with force because you do force balances on all these. This is like the Wilhelmine plate, stick a plate in, pull it out, measure the contact angle. The cosine would be the force, the vertical force. Then the force of you pulling it out has to balance that liquid force that's pulling it down. And you can write an equation for that and get the contact angle, basically this equation, right? You balance the two forces. This is for a capillary, same thing though. Like you get cosine of the angle will give you the force up and down, then the liquid head above the liquid in the solution is going to be a force down. So you have rho GH force, and then this force from the surface tension, and then that gives you this contact angle, right? So, and then this there's also this tilting plate process where you can do that. And you can also do a droplet. This is like the normal way to do it, is to put a droplet on a surface and then just measure the contact angle. Also, it's a force balance on the surface of this thing. And it's also cosine of the angle, gives you the forces on the surface, right? So anyway, however you do it, measuring this angle can give you the surface energy of the solution, right? I went through also this law of sines business can give you kind of the surface energies for where 3 phases meet. So you have the alpha beta phase, and then the gamma. So the other angle, like this angle, is going to be those 2 phases surface tension. Like they're paired up with the law signs from the kind of some triangle involved in this thing. But basically, this is a rule for if you look in a micrograph and you can measure these angles, and then you can tell what the relative surface energies of the three phases are from that. If you know one of them, you can get the other two. That's kind of the idea, I guess. But if you have the three angles. So there's a bunch of these like force balance things. There's a lot of papers where they're kind of use this to analyze the composition of phases just from the angles, contact angles. All right, so we kind of looked at that, I guess, last time. Then we looked at, actually we did a lot. We looked at the Gibbs stuff last time. So kind of the Gibbs-Thompson equation. So this basically ends up that there's three forms of this thing somewhere here. That's homogeneous, heterogeneous. Somewhere here is the three forms of the Gibbs-Thompson equation, not there. This isn't it. So there's size. That's one of them, but let's see. Someplace I have these listed in here, but exactly see it. This is so basically the idea of this is just you're going to have like exponential of energy over kT, and that's going to be some probability. So here's like the pressure, the vapor pressure versus the infinite surface vapor pressure for different sizes R. And then basically the top term is going to be energy. So you have this is force, this is energy per area. So you end up with energy per volume out of this times the molar volume gives you just energy divided by RT. So exponential of that gives you this pressure for a droplet of size R. That's kind of the idea of this. One of the Gibbs-Thompson equations. So how droplet pressure changes with energy, surface energy. So so it's kind of, this is kind of like if you take the Laplace equation, the 2 sigma over R, and then do the derivatives of it, you can get the same thing. You can do a derivative form of it. So I talked a little bit about boiling and like bubbles and how that's important to nuclear reactors and things and metals, degradation in nuclear reactors. And then there's this business of crystallizing from solution. So depending on the supersaturation that you reach above the crystallization concentration, then you produce smaller particles for higher supersaturation. So it's basically like 1 over the log of the supersaturation gives you the particle size. And it's related by this surface. So that's kind of the first kind of Gibbs-Thompson is this business of pressure for droplets. The second is kind of this concentration dependence on particle size. And the third thing is this temperature, not this stuff. Not this stuff. It's beyond this. Where is the third thing? Oh, sorry, let me just skip through here for a second. How come I don't have that slide here? That's way too far. These are actually listed on one slide. Absorption. The slide is called Gibbs-Thompson. 3 forms of Gibbs-Thompson. Right, so the third thing is this thing. So basically, if you write out the free energy, I think we've gone through this already, but if you write out the free energy is 0 at equilibrium, and you have the enthalpy minus the entropy, so minus Ts, and delta S is delta H over T infinity. And then you have this surface term, and then you take the derivative and set it to 0, and then you can solve this and find that this this temperature ratio ends up being, let me see, let me just do this here. I didn't do this yesterday last time. So this is kind of the third form of this. Hmm. Does not have the auto tune. There. All right, so we have that, right? That's our SUV. And you have DG is SVT, or no, G is HST. So G equals H minus TS. There's a negative to it, right? So, and then so delta G is delta H minus T delta S. And then if you say at equilibrium at T infinity, that equals 0, so then you have the delta H equals delta H over T infinity is delta S. So we'll end up with that. And you can plug that back in. You can say delta H times 1 minus T over T infinity, that thing. And then if you want it, and this is volumetric, so if you want to get the actual value, you multiply by the volume, which is like R cubed. And if you want to add in the, so for an actual thing at size R, then you would add in the R squared times the surface energy, sigma or gamma. And then if you want to find out what's the size, so you can take the derivative of that. You take the derivative of this finite size for energy. So this is an infinite size. And then you'd find like 3 times delta H times this 1 minus T could be like T, see, this would be T infinity. So it could be T infinity minus T over T infinity, if you wanted it to be, right? I multiply by T infinity there. And then times R squared plus 2 gamma, and then 2 gamma R, so you can get rid of that and set that to 0. This would be derivative of delta G, the R, set that to 0. And then you can solve that for R. So R is going to be 2 gamma over delta H 3. I don't know where the 3 comes from. And then this T quenched up, like T infinity minus T. So that's delta T, the quench depth that you did, and then times T infinity. And so that gives you the, for a certain quench depth that you do. So you're going to crystallize as a crystallization temperature. In order to really crystallize, you have to go below that temperature. Well, the further below you go, then you get smaller size phases from it. That R gets smaller. And so that's one form of Gibbs-Thompson. That's kind of this. That's kind of this business. It's whatever it says here, but it ends up giving you this sigma over delta H, the ratio between the surface energy and the bulk enthalpy of formation, and then the quench depth. So the deeper the quench depth, the smaller the particle. So all the 3 forms are basically the further you go from equilibrium, the smaller the particles you get. So you can crystallize at a deep quench, you can get really small particles. If you crystallize at a deep concentration quench, so you have much supersaturation, you get small particles. And the same with the pressure for bubbles thing. But,
So when you had the B in the equation instead of the geometrical factor?
yeah, B, depends on if it's, so B for if you crystallize platelets, it would be 2 sigma. It's going to be different numbers. It's a constant depending on what the shape is of the crystal that you form. For a cube, I guess it would be 2/3 for a cube, and then 2 for a platelet, and the rods will have another number. So basically, depending on the shape of the crystal. Yeah, so that's just a number. It's a fixed number. Oh, 2 to 6. So this thing it's called Gibbs-Thompson. If you do cubic crystals. And then it's called, for platelets, it's called the Hoffman-Lorentz equation. It's the same equation. And and this guy Hoffman was a polymer guy, but he was like a famous kind of political scientist, and he was like friends with JFK and stuff. He was an advisor to the president and all this stuff. So anyway, so the equation he had was kind of like the same as the Gibbs-Thompson equation, yeah. So it's kind of funny. It's almost just B is a different value. But anyway, he did some other things too, but the guy only had like 60 papers, you know. I mean, and then and he was pretty famous. He didn't win the Nobel Prize or anything, but pretty famous. And then you look at a guy like Oswald, you know, 600 papers, and it was like 100 years before that. And all the papers were handwritten, right? They weren't like, so it was pretty hard to publish that. So it's kind of funny, like maybe the numbers went down or something and went back up. Now it's like you need 600 papers, whatever, you know. Like a lot of people have huge numbers of papers. So anyway, whatever. I just thought it was kind of interesting. The guy I thought was really famous. And I looked up his publication record. It was like 60. There are like 10 of them are seminal papers for this kind of thing, crystallization of polymers. Then so they basically wrote the book on crystallization of polymers. Also at that time there was a lot of arguments, you know. So you'd see a lot of debates over things. Anyway, so like bloodthirsty arguments. People, instead of politics, they would argue about like what was forming at this, like this business about what nucleates at the surface before it crystallizes. You know, it's like, well, it could matter, I guess, you know, but so I think let's see. So this is beyond. So let me go back then again. Sorry. So then I talked about last time I went through this, and then last time I also said like nucleation, that you can have homogeneous or heterogeneous nucleation. So basically you end up with half the size, literally half the size for surface nucleation. And the energy isn't exactly half. It's like, I don't know, 9/80ths. So whatever that is. I guess it's 1/10, right? Or if that was 10, that was 100, it would be 1/10. Something like it's less than half for the energy. So it's much more likely that you get heterogeneous nucleation. So you might want to mention that in commenting on this paper at some point. You know, like he's using this model for 3D crystallization. It's not, it doesn't make any sense. Like, why did he even point that out? You know? So I already, like, this is a plot of the free energy. So there's going to be a maximum. If you plot free energy versus size, and then that gives you this critical size, the magic size. Plug that back in, you get the magic energy for the peak. And then from that, you can calculate the kinetics and some other things. Right. So basically, on the left side of this, the particles won't form. Basically, there's a perfect spot where the things will form. And if you go above this, where the free energy goes below zero, then that's spontaneous. Everything's just going to automatically form. But if you go below this, you do the derivative of this, you find out that it's not possible to form below that size. So that's a critical point where the things won't form below that. All right, and that can give you Ostwald ripening if you want to look at it that way. I think Ostwald didn't have Gibbs. Gibbs was after Ostwald, so I don't think that he had Gibbs to go by to get this equation. But I think somebody rethought it and got this equation for Gibbs, which is based on this critical size thing. So, which is the same as the Ostwald ripening equation. That's a map of what the energy looks like for homogeneous, heterogeneous. And then this is from a different book, the same thing. And this is Adamson's when he goes through the same thing. So Adamson's book is up there. That's like the first for physics. So there's like the first business is from our book, I think, and then the next thing is from some book on crystallization from solution, and the third thing is from this book by Adamson, which is physical chemistry. So the solution one's like, I don't know, it's like making pigment particles and things. And the first one is kind of metallurgy. The third one, and it's all the same thing, but the nomenclature is a little bit different. So I kind of threw them in the notes. It ends up being the same stuff. So it's probably not. He's talking about this from a gas phase. Adamson's starting with a gas phase, and he's talking about this kind of what's called a collision kernel in some later papers. This Z is kind of the idea that you have two things collide in the gas phase, and they can form a solid phase from the gas phase. Like if you're burning some organic thing and making a ceramic from it to make nanoparticles, and then like how you make titanium and silica. So this Z becomes important in some fields, this collision kernel thing. Like it's basically the dynamics of how molecules collide to form a solid. And then so that's going to be a function. That's going to be kind of a function of energy and things and temperature. And then this delta G max is a thing from the free energy plot. So basically the probability, Boltzmann probability is going to be the free energy by KT. Will give you the probability that the thing forms a crystal, but in order to form a crystal, it also has to have a collision. Like the atoms have to meet the surface. So you have to have this prefactor. So Adamson goes through that business. He kind of goes through like how things crystallize from gas phase to solid. Preforms of Gibbs-Thompson. And then our book goes through a lot on this business, which I guess I'm going to skip for now mostly. But he talks about you have this interface. So you're actually going to have like some sigmoidal. So you have alpha phase and beta phase, right? They're interacting with each other in interface. Then you have a kind of a depletion of one component and the other near the interface. So that the interface isn't just a straight line, it's got this gradient to it. Right. So you have to define some kind of line where the interface is. Depending on where you put that, your amount of excess components at the interface changes. So that's kind of the whole thing. But there's kind of a magic position, or there's a way to look at this where you don't have to define the line. Right. So that's what the chapter in the book talks about that. I haven't really found a paper where that's important. I don't know why that slide's here, but anyway, so it's in the chapter. I guess we can kind of skip it for now, but he ends up giving this relative absorption number. So the gamma depends on where you put this cutoff point, and this relative absorption doesn't, which is the amount at the interface of one component minus the other component, and then the concentrations of the bulk phases. So, and it's derived in the book, this equation. Again, like, I'm not sure exactly how important this is, because I haven't exactly seen this in papers. So I'm not really pushing that too much, but it is in the book, so I put it in the slides. All right, so let me skip that. I wanted to talk about this business. So this is like the machine that you use. So you have a powder, right? You made like nanoparticles. You want to know like how big are the nanoparticles. That's kind of the first thing you do. So you can put it in a TEM and kind of look at it, but that's got to be under certain conditions. Like, I don't know, to prepare the sample, there's various things you have to go through. You have to put it into an alcohol and deposit it onto the thing. That can change the size, for instance, right? So here, this is a technique. This is kind of another technique, kind of the main technique that people use to figure out how big is the stuff that you made if you're trying to make small things. So there's another technique called pycnometry that's kind of almost similar to this, where you put helium. It's called helium pycnometry, and you put helium in and you condense it onto the material, and then you measure this kind of the porosity of it by the amount of helium that goes into it. It's kind of a similar thing. In this case, you either use nitrogen or argon, and you're gonna cool it down with liquid nitrogen, so you can get like liquid nitrogen or liquid argon in this thing, right? So you're gonna pressurize it, and then you're gonna cool it, and then you hope you're condensing the gas onto the surface of the thing. So that nitrogen, I think, has a size of I think it's like 8 angstrom N2. And then the argon has a smaller size. I think it's like 6 or 5 angstrom. Right. So depending on what size, so you can have a surface that's going to have, I think there's a picture of it here, but basically the surface isn't smooth, right? So depending on what gas you use, there. So let's say you have a surface like that. Right. I mean, this is a surface, if that's a blow up of something that's like, you have a particle like that, and that's a blow up of, say you have just a bunch of stuff. You cook this, and you blow it up, and this thing's going to be on the order of like 100 nanometers, and these pores are going to be on the order of like 1 nanometer. Right. So basically, the nitrogen is going to be 0.6 nanometer, kind of a sphere. It's actually like 2 nitrogens, it's just like a sphere. So how it can like park in here, right? So you're going to try to cool down the nitrogen and let it sit on that. And then you're going to actually like weigh this thing. You can get the weight before and after, and the difference is going to give you the number of nitrogens that went onto it. You know, they're like 0.6 nanometer diameter, so you can calculate the surface area of the surface, kind of the profile of a nitrogen atom, and then by multiplying how many nitrogen atoms, and you get how much the surface area of the stuff is. And you know the weight of this, so it's per gram, so it's going to be meters squared per gram. Then you need to know the density if you want to know meters squared per volume. And typically that number is going to be like 100 meters squared per gram for silica, like SiO2 nanoparticles, or titanium, right? So that's a lot, like 100 meters squared per gram would be 100 meters squared is a football field, and it's in 1 gram of stuff. That's kind of the idea. Right? So there's a lot of surface area in these materials, a lot more than what. So anyway, so that's the machine that you use. So anyway, so you're gonna do that process of condensing the gas onto it. And again, like depending on what the size of the surface asperities are, and then you can also have, so there's going to be a lot of nuances to this. So people just do this technique for their professional life. They just do this one thing, you know. So you can imagine they've developed a lot of different things. So it can be like that, or it could be like say like that, you know. So your nitrogen might be like this or like that. So if your nitrogen is this big thing, then it won't fit through the hole, right? If it's small, maybe it can kind of fit through the hole. No matter what, like once you absorb it, and then say you desorb it, so you can look at the weight as a function of adsorption and desorption. So you can do it hysteresis curves. You can kind of do the temperature, and you can go up. So you can go up and you can come back down, and it might not be the same because of this business that you have these bottleneck things, so that some of it gets trapped in here and can't get out, like it's having a hard time getting out. So you got a hysteresis in the curve, right? So there's a lot to this kind of absorption desorption thing using this machine that you're going to. So and then also you can have another kind of pore. So you could have just closed pores. There's no way that the nitrogen can get into it at all. That's called a closed pore. So when you make a material, it could have a much lower density than what you thought, or so basically you're going to get this V by S number, or S by V number, the surface to volume ratio we were talking about from the correlation function, right? So if you do this for like 4/3 pi r cubed and then 4 pi r squared, you end up with like 6. If you go change r to d, 6V by S gives you this Sauter mean diameter, which is equivalent spherical diameter of your stuff, of your pores in your stuff, or the particle size kind of. So Sauter mean diameter of 6V by S is like a typical measure of the size of things. It's a nice size because volume is like the average of cubed size, and then surface is the average of the squared size. So these are what you call lower order moments. So if you have a distribution, say you have a distribution of particle size like that, right? And then the normal would be the first moment. Right, the average size is that. The second moment's gonna be like a higher number, the third moment's a higher number. But if you do something like the weight average, this thing becomes like the eighth moment or something like this. So the higher the order of the moment, the bigger the number, and the less reflective it is of the whole curve, of the distribution curve. So you want to have low order moments. This V by S are low, those are low order moments. That's a useful number to figure out what the actual size is. I mean, say you have a beach, full of sand, and then you have rocks on it, boulders. But say you measure the rate of gyration of that. Well, rate of gyration is the eighth moment over the sixth moment. Rate of gyration squared is the eighth moment by the sixth moment of it. So a number like rate of gyration from light scattering or neutron scattering gives you the boulder size, and this measurement gives you the actual sand size. So it's kind of useful to have a low order moment way to measure the size of things. Anyway, so that's the machine, and the technique that's used to do that is this Langmuir absorption thing. So you say you have a surface, and again, like you're saying that it can fill up. So you have sites, your things are gonna, like your nitrogen atoms are gonna come in and pop on it, or this could be like, it could be just the bonds on the water affiliated with the calcium carbonate. It's the same story. So you'll see this Langmuir model like over and over and over again. Like people talk about a surface and then something happens, catalytic reaction happens to the surface, something comes up, it reacts. Like how can it fill the surface and have the reaction happen? So it's a platinum catalyst in a car converter to get rid of NOx and exhaust gas or something, right? So it's going to be the same equation that they'll use to talk about it. So you can imagine there's some problems to this. One problem is it assumes a monolayer. Like you assume you're just going to get one layer of things absorbing onto it. It assumes there's a fixed number of sites. And then it assumes the surface is completely accessible. So there's a bunch of nuances to this model, right? So you just say like you have your gas, it's going to turn to absorb species. There's some kind of, so you're going to have the sites that you have on the surface, the gas, and they combine to form this absorbed thing, right? And then once it's absorbed, it's a done deal. It's finished. It's not an equilibrium. And then, so it's basically the balance between, you can say you have solvent 1, solute 2, surface bound, bulk free. So then you have 1 and 2 bound, unbound. You start with, or bulk, which is free. So bound is a bad word to use here, but anyway, surface and bulk, right? So A1, so you solute, the thing you're absorbing is this 2. So A2, that's surface bound, that's your product. And then A1, so you're removing the solvent from that site. So the bulk solvent and the surface bound stuff is the finished product. And then the free thing that you're trying to absorb, and then the absorb thing you're trying to put back into solution, the majority component, right, gives you this K number. And then you can write, the thing you're interested in is the absorbed 2, so the solute absorbed, which you call this theta. So typically in this Langmuir equation, you have theta, which is a surface coverage, right? And that's going to be, if you rewrite this equation, you can solve for A2, you end up with this equation, basically. Right, so you just have the, it's going to be this kind of behavior. So as you change your free, so B means free, concentration and solution, then you get this will end up giving you this decay curve, this thing. It'll end up looking like this, like the coverage, Langmuir coverage, and the concentration will look like this sigmoidal thing from that equation. That's the idea. So there's kind of 2 ways to get that. One is you can get it from this kind of equilibrium constant model, or you can get it from a reaction rate model, like a rate of absorption. There's another way to get it, but so basically there's 2 ways to get this same equation. So it's a simple equation. It's called the Langmuir equation. There's also a journal named after the guy Langmuir, and there's also a Langmuir trough. Like if you do surfactants, you have small amount of surfactant on a surface, and then you have a kind of a bath where you put it in. You can put a like a rubber windshield wiper, and it can squish the surfactants. You can measure the force that it takes to squish the surfactants. So you can have a 2D kind of pressure. You can do a phase diagram for the surfactant molecules on the surface. It's called a Langmuir trough, right? So you get like plots of pressure versus area, like PV plots for surfaces with that. So Langmuir was a guy that did, like a British guy, I think also 1800s, but right. So this is the equation that you'll see over and over again. And the other, so this assumes like you have a monolayer that's absorbing in a fixed number of sites, right? And then whatever other assumptions here, right? So the natural thing is like if you had bilayers forming. So if you look at the data from this machine, it's going to be like the amount absorbed. So you weigh the thing before and after, you figure out how much nitrogen absorbed. And then versus the pressure that you put for the nitrogen, it condenses, follows the Langmuir equation perfectly. That's called type 1 isotherm. Then it could also like, it could fail and like suddenly kick up, meaning that you fill up certain kind of sites, and then there's a higher pressure where you see another kind of sites form. So that could be another layer forming on top, like the secondary layer, or it could be some other sites, right? So that's a type 2. And then if you have multiple, so this assumes there's only one kind of absorption site. If you have multiple types of absorption sites, you get a type 3 curve. And then type 4, what's type 4? Mesoporous structure. Like you have 2 plateaus. Type 5, type 4 is common, type 1 is common. And then so type 4 means you have you have different size. So you have a structure where you have a convoluted structure, and then you have absorption on this kind of nanoscale and kind of packing on a larger scale. Like meso means like a larger scale pores, right? So anyways, there's different types of these isotherms. And then so in order to take care of that, usually people are not using the Langmuir equation. That's the point. They're using this BET equation, which takes care of this multiple layer absorption. So you can see BET kind of has a Langmuir behavior early and then kind of kicks up. BT is pretty complicated. The Langmuir is pretty simple. BET is pretty complicated, but it has an equation. And then there's this thing called the Freundlich absorption equation, which has no theory at all. Freundlich is just, it's a power law dependence. That's it. So it's just like there's no theory to it. BET has a theory that you have like monolayer, bilayer, whatever, and they interfere with the absorption. But when you do that, the mathematics of it gets to be really complicated, right? So mostly people just use BET equation. The Freundlich equation is just like a free-for-all. Like I'm giving up with equations. I'm just going to say it's a power law, and I'm not going to try to explain it. I'm just using this, and it kind of fits the data, and that's it. And then you get these numbers from it that don't necessarily reflect anything in physics, but you can predict the absorption curve. So there's three common equations. The most popular is this BET equation. Like people talk about the BET surface area, for instance. So just use it as if it's a term, like it's a technique, versus the technique is actually gas absorption using a machine like this. And then Langmuir's the original equation that describes the simple behavior of the absorption. And then BET is this kind of more complicated function that allows for multiple layers absorbing, like first, second, third. So you can see it's like 1, 2, 3, etc. So it continues on, and you end up with, it's a different equation. That's all, slightly different. It's more complicated. So, and this just showing like if you have this kind of bottleneck porosity, then you can get this hysteresis and the absorption desorption curves for these things. So you have like Langmuir behavior, then you get this bottleneck thing, and when you desorb, it doesn't follow the same curve, right? So it's got to do with deviations from that. That's the thing I wanted to show that I kind of tried to draw. But this would be like a bottleneck, right, that would cause hysteresis. You can see there's different phenomenon people talk about. I forget. I think this is from Adamson's book, but no, it isn't, because it's 9. So this is from the Heimet's book on surface chemistry. The Adamson book is in Roman numerals. That's why the chapters. So this thing's in, this is from the High-Notes book, which is on the webpage if you want to see it. Then we got like 8 minutes. So I wanted to kind of go through this thing too. So basically the other in polymers, right? This is a topic that has to do with surfaces. So basically, and it's different than Langmuir absorption. So basically there's you can make polymers that have fixed, so you can make like styrene, butadiene, SBR rubber, which is a tire, right? So it's blocks where you can produce like a styrene chain of fixed molecular weight, then a butadiene rubber chain of fixed molecular weight, then a styrene chain. So the styrene is like a glassy polymer and the butadiene rubber is a rubbery polymer. So if you can get the domains right, and then the styrene will naturally cluster together, say like the black domains here, then the white would be rubber. So that means you have these kind of glassy crosslink sites that connect the rubber together. So, and you can melt the polystyrene 110C, so you can extrude this thing and then it can, so it's a thermoplastic elastomer, right? So it's also, you can make a tire with it. When you make a tire with it, you actually cross-link the rubber. So you put like sulfur in, so you can't extrude and melt a tire made from SBR rubber. You can make an SBR thermoplastic elastomer that you can extrude. It could be recycled, yeah. But a tire can't be recycled ever because it's without burn, you can burn it. That's what you can do with a tire. You can grind it up, put it on a playground, or you can burn it. And that's kind of your options, yeah. Or you can cook it at really hot temperature and make diesel from it, which is basically kind of burning it, you know. So it's limited what you can do. But anyway, because you can make tires with this stuff, and they actually make like huge amounts of this material like now, because like every tire you have, the tread is SBR rubber. So you can imagine like your car has like, I don't know what a tire weighs, but basically like 20 or 30 kilos or something of rubber. And then all the cars, and then all the tires that have ever been made, you know. So there's a lot of this stuff around. So even though it was kind of a nuance. Anyway, so as you change the lengths of those two chains, so as you say, phi A would be the length of one chain relative to the other, like the number of units in the A versus A and B. Then you go through this kind of phase diagram where you get, this is chi, so this is 1/t, so this is separating when you cool it down. But you get layers. This looks a lot like the spinodal structure. When you have equal amounts, you get layers. If one's more popular, you get cylinders. And if one's really more popular, you get spheres. You get that thing on either end. And the phases would shift between the two. Right. And then typically people will do like diffraction or small angle scattering on this and get diffraction peaks from it. And the peaks reflect the like morphology of the structure you get out of it. You can do TEM, but the problem is the 3D structure. This is a 3D technique. TEM's like 2D. So you have to do careful slices in different directions to really determine the difference between beads and rods. So, you know, when you slice rods that way, it looks like beads. Anyway, so you can use a free energy thing to get the whole package on this. So you just write H minus T delta S. Delta S is going to have entropy associated with fixing these chain junction points at the interface between the phases, and then the configurational entropy of the chains wiggling around, right? So the same with delta H also has this interfacial term where you fix the chain links at the interface in a region of a certain area of the interface and a certain thickness of the interface. So the area divided by the volume of that interface by the volume of the system times the interaction, like the Hildebrand interaction times KT gives you this chi has 1/KT in it. So it gives you this enthalpy of the interface. Then there's the other kind of, this is a normal Hildebrand term, and then the composition A, composition B thing for enthalpy. Right, so enthalpy's got an interfacial and a bulk, and the entropy also has interfacial and bulk. And all the equations you write for that are based on the surface area of the phase. The surface area of the phase depends on the size of the domains that you form. So if you take the derivative of this, find the minimum of the free energy, set it to 0, then you can solve for what the size of the phases are. That's the whole idea behind this this hill fan theory for block copolymers. So it can be calculated exactly like what the size of the phases are versus size of phases versus the molecular weight of the blocks, or versus the temperature, or whatever you want. Basically, you can predict the whole behavior of these kind of seemingly complex systems just with a simple Hildebrand model, with a couple twists to talk about locating the junction points at the interface. That's mostly the idea of that. There's book, if you're interested in that, there's books on it on the web page. You know, there's let's see. This thing's not going there. It would go there if I just said new. Because it's right here. Just in the surfaces section at the bottom too. So there's the bottom of this is ice, supercritical, blah, blah, blah. This Rubenstein Colby book has stuff on that. This Meyer book is only about just exactly about this, from 69, about block copolymer phase size. The Strobel book covers that subject too, and this Hamley book is only about block copolymers. These are all just that. This book and that book are only about thermodynamics of these phase separating systems. The reason there's so much interest is that you can put a water soluble chain and non-water soluble. You could swell the water soluble with a ceramic material, right? And then you could form the ceramic phase in the water soluble part. And you could pyrolyze off the unwater soluble part, like the polystyrene. Then you'd have a nanostructured ceramic that would be like rods, discs, sheets, whatever you want. And the thickness of those things is going to be like 5 nanometers. And you can tune the size exactly using that hill fan theory, right? So you can make like anything you want with this. So people make anything they want with it, basically. This uses a template. Synthetic zeolites for catalysis in one area where they do that. But there's a bunch of other areas where people are using block copolymers to just tune ceramics structure. Not sure if they've done it with metals. They probably have. There's probably some metals where they use, if you can figure out a metal precursor that can go into whatever the phase is of the other thing, and then just use that as a template, and then just burn off the plastic, and you end up with the thing you want. You know? Anyway, so that's about it. Sorry to kind of zip through that stuff, but hopefully it's okay. And I also skipped. I might go back to that other part on Tuesday or whatever. Hopefully the homework won't be too challenging this week too. So it seems like it's been, like spinodal is the hardest thing. You know, well, not necessarily. Heat capacity is harder, I think, but basically spinodal is a hard thing to look at. And then this stuff should be simpler. So, all right.